The intriguing link between quantum field theory and time travel. Quantum field theory, a framework that underpins the very fabric of our universe. At its core, it posits that everything in existence arises from fundamental quantum fields that permeate all of space. Unlike classical physics, which describes particles as distinct objects moving through space and time, quantum field theory, QFT, treats particles as excitations or disturbances in these ever-present fields. These fields govern the interactions between all known forces of nature, from electromagnetism to the nuclear forces that hold atoms together. One of the most fascinating aspects of QFT is the concept of virtual particles. These are particles that exist only fleetingly, emerging from the quantum vacuum and vanishing just as quickly. While they may seem ephemeral, their effects are far from negligible. They contribute to real, observable phenomena such as the Casimir effect and Hawking radiation, both of which stem from the intricate dance of quantum fluctuations. These fluctuations hint at an underlying reality where energy and matter are not as static as they appear. Time travel, an idea that has fascinated and confounded scientists and thinkers for generations. It is not merely a figment of human imagination, but a concept that emerges naturally when exploring the deepest realms of physics. Time is not absolute. It stretches and contracts depending on motion and gravity. This has been firmly established by Einstein's theories of special and general relativity, which describe time as part of a four-dimensional fabric known as spacetime. According to these theories, time can be manipulated under extreme conditions, making the possibility of time travel at least theoretically plausible. Yet, time travel is not without its paradoxes. One of the most famous is the grandfather paradox, which raises a fundamental logical contradiction. If one were to travel back in time and prevent their grandfather from meeting their grandmother, would they ever be born? The implications of such paradoxes suggest that time is not as straightforward as it seems. Various solutions have been proposed, including the many-worlds interpretation of quantum mechanics, which suggests that altering the past simply branches reality into a new timeline, avoiding paradoxes altogether. The connection between QFT and time travel arises from their shared foundation in the laws of quantum mechanics. While classical physics dictates a rigid progression of time, quantum mechanics introduces an inherent uncertainty. Particles can exist in multiple states simultaneously until observed. They can even interact non-locally, instantaneously influencing each other across vast distances. These peculiarities suggest that time may not be as linear as it appears. Could the behavior of quantum fields provide a loophole in the structure of time itself? The nature of virtual particles, the fluctuations of the quantum vacuum, and the interplay of fields suggest that the flow of time is not as rigid as once thought. The key question then becomes, can these quantum effects be harnessed to influence or even traverse time? Physicists have long considered the possibility of manipulating time using quantum principles. One approach involves wormholes, hypothetical tunnels in spacetime that could connect distant points in both space and time. Wormholes have a strong basis in Einstein's equations, but their practical existence remains uncertain. Some theories suggest that if a wormhole could be stabilized, it might allow for time travel. However, maintaining an open wormhole would require exotic forms of matter that violate known energy conditions. Another avenue for exploration lies in time dilation. According to relativity, the faster an object moves, the slower it experiences time relative to a stationary observer. This effect has been confirmed experimentally, with atomic clocks on fast-moving spacecraft ticking at a slightly slower rate than those on Earth. If time can slow down under extreme motion, could quantum fields play a role in manipulating this effect on a fundamental level? The deeper one ventures into the quantum realm, the more uncertain time itself becomes. Some interpretations suggest that time may not even be a fundamental property of reality, but rather an emergent phenomenon arising from deeper quantum interactions. The interplay of quantum fields could hold the key to understanding the nature of time and whether it can be traversed. To fully grasp this potential, it is crucial to recognize that QFT does not operate in isolation. It interacts with relativity, thermodynamics, and even information theory, each offering its own perspective on time. Quantum entanglement, for instance, has been proposed as a mechanism that could allow information, or even causality, to transcend time constraints. The distinction between past, present, and future is only a stubbornly persistent illusion. These words, attributed to Einstein, encapsulate the mystery of time itself. If the flow of time is an illusion, could QFT be the tool that unravels it? Despite the theoretical promise, time travel remains an unresolved question in physics. No experimental evidence has confirmed its feasibility, and many of the necessary conditions remain speculative. However, the study of QFT continues to push the boundaries of what is possible, offering glimpses into a reality that defies conventional understanding. The potential link between quantum fields and time travel is a topic of profound significance. While many questions remain unanswered, one thing is clear: the fundamental nature of time is far more intricate than classical physics suggests. Quantum mechanics has already redefined our understanding of reality, and if time is indeed malleable at the quantum level, then the doors to entirely new possibilities may one day open. Quantum field theory provides a framework that allows for effects beyond classical intuition. It suggests that time is not a fixed river flowing from past to future, but a more dynamic and intricate structure woven into the very fabric of the universe. If this is true, then exploring the quantum nature of time may eventually lead to discoveries that reshape our understanding of existence itself. The idea of time travel is often met with skepticism, yet the principles underlying modern physics do not rule it out entirely. The search for answers continues, driven by the quest to understand the most fundamental aspects of reality. Whether or not time travel ever becomes a reality, the exploration of these concepts will continue to challenge and expand the boundaries of human knowledge. Delving deeper, QFT and its time-bending potential. The nature of time, a concept deeply embedded in the fabric of the universe, yet one that remains elusive. Quantum field theory, QFT, which describes reality at the most fundamental level, may hold the answers to questions that have puzzled physicists for centuries. Could quantum fields play a role in bending time? Could the strange phenomena predicted by QFT provide a mechanism for time travel? These questions drive researchers to explore the very limits of theoretical physics. One of the most intriguing possibilities in the realm of time travel is the existence of wormholes. These theoretical structures, also known as Einstein-Rosen bridges, arise from the equations of general relativity. A wormhole is essentially a tunnel through spacetime, connecting two distant points in the universe. If one end of the wormhole were positioned near a strong gravitational field, such as a black hole, it could experience significant time dilation relative to the other end. This means that a traveler entering one side could potentially exit the other at an earlier or later time. Theoretically, wormholes could provide a pathway for time travel, but there is a major obstacle: stability. Classical physics predicts that any naturally occurring wormhole would collapse before anything could pass through it. However, QFT introduces the concept of exotic matter, substances with negative energy density that could counteract this collapse. The Casimir effect, an experimentally verified phenomenon, demonstrates that quantum fluctuations in a vacuum can create regions of negative energy. If negative energy could be harnessed in sufficient quantities, it might be possible to hold a wormhole open, allowing for traversable time travel. Even if wormholes are feasible, their existence alone does not guarantee practical time travel. The interplay between QFT and general relativity must be considered in greater depth. According to relativity, time is not a fixed entity but is influenced by motion and gravity. A phenomenon known as time dilation demonstrates this effect. Time dilation occurs when an object moves at speeds approaching the speed of light or experiences an intense gravitational field. The closer an object is to a massive body, the slower its internal clock runs relative to an observer in a weaker gravitational field. This effect has been confirmed through experiments involving high-speed spacecraft and atomic clocks. If an astronaut were to spend several years near the event horizon of a black hole and then return to Earth, they would find that far more time had passed for those who remained behind. How does QFT fit into this picture? Quantum fields do not exist in a vacuum in the traditional sense. Rather, they interact with the curvature of spacetime. This means that the fluctuations of these fields could, in principle, be used to manipulate time dilation. Some researchers have speculated that quantum fields could be engineered in a way that creates artificial time dilation, slowing down or speeding up the passage of time in localized regions. One potential avenue for exploring this concept is the unravel effect. According to QFT, an accelerating observer perceives a vacuum differently than an observer at rest. Specifically, they experience what appears to be a thermal bath of particles, as if they were surrounded by radiation. This suggests that the vacuum state of a quantum field is not absolute but depends on the observer's motion. Could this effect be leveraged to manipulate time perception or even create artificial gravitational fields? While the idea remains speculative, it highlights the profound relationship between QFT and the nature of time itself. Beyond wormholes and time dilation, another quantum phenomenon hints at the possibility of time manipulation: the interaction between virtual particles. These ghostly entities exist for mere fractions of a second, flickering in and out of existence due to the uncertainty principle. Although they cannot be directly observed, their effects are measurable. They contribute to processes such as Hawking radiation, which describes how black holes slowly evaporate over time. Could virtual particles influence the flow of time? Some researchers suggest that these fleeting interactions may play a role in the structure of spacetime itself. If virtual particles contribute to the fabric of reality, then their influence on time could be more significant than previously thought. Theoretical models propose that an advanced civilization with sufficient control over quantum fields might be able to manipulate these fluctuations, effectively warping time on demand. Even within conventional physics, time is not as rigid as it appears. The Wheeler-DeWitt equation, a key component of quantum gravity theories, suggests that time might not be fundamental at all. Instead, it may emerge from deeper quantum processes. If this is the case, then controlling quantum fields could provide an unprecedented level of control over the flow of time itself. There is another aspect of QFT that warrants exploration in the context of time travel: the concept of vacuum energy. The vacuum is not empty. It is teeming with energy fluctuations. If this energy could be manipulated, it might allow for distortions in spacetime. One speculative idea, known as the Alcubierre drive, proposes using a bubble of negative energy to contract space ahead of a spacecraft while expanding it behind, enabling faster-than-light travel without violating relativity. If such a mechanism were possible, it could potentially be adapted for time travel. While these ideas are deeply speculative, they raise important questions about the fundamental nature of time. Could time itself be a malleable property, one that can be controlled through precise manipulation of quantum fields? So, what are the limitations? One of the biggest challenges in studying these possibilities is the lack of experimental evidence. Many of these concepts exist purely in the realm of theoretical physics, with no concrete way to test them using current technology. However, ongoing research in quantum mechanics and general relativity may one day provide insights that bring us closer to answering these profound questions. The universe is not only stranger than we imagine, it is stranger than we can imagine. This quote, often attributed to J.B.S. Haldane, reflects the mystery surrounding time and the quantum realm. If our understanding of the universe is incomplete, then the nature of time may be far more complex than we currently realize. Despite the many challenges, the exploration of QFT and its relationship to time remains one of the most exciting frontiers in physics. If time can be influenced by quantum effects, then the implications extend far beyond theoretical speculation. They could revolutionize our understanding of causality, free will, and the very fabric of existence. While time travel remains a distant dream, the physics governing time continues to be explored with increasing sophistication. From wormholes to time dilation, from virtual particles to the fundamental nature of spacetime, each new discovery brings us closer to unlocking the secrets of time. Whether or not humanity ever achieves the ability to move through time at will, the study of these phenomena deepens our understanding of the universe. The mysteries of time and quantum fields are far from solved. But one thing is clear. The deeper we look, the more we realize that reality is far stranger than we ever anticipated. The role of quantum entanglement. Quantum entanglement. A phenomenon so perplexing that Einstein famously referred to it as spooky action at a distance. At its core, entanglement describes a situation in which two or more particles become intrinsically linked, such that the state of one instantaneously influences the state of the other, regardless of the distance separating them. This phenomenon has been experimentally confirmed countless times, proving that entangled particles behave as a single unified system even when separated by light years. Could this strange connection hold the key to time travel? If information can be exchanged between entangled particles instantaneously, does this violate the constraints of time as we understand them? The potential implications of entanglement challenge the very fabric of causality, prompting physicists to reconsider whether time itself is a fundamental limit or a malleable construct shaped by quantum processes. In traditional physics, the concept of locality is a cornerstone principle. This principle asserts that objects can only be influenced by their immediate surroundings and that signals cannot travel faster than the speed of light. However, entanglement defies this notion. When two particles are entangled, measuring the state of one instantaneously determines the state of the other, no matter how far apart they are. This suggests that quantum information does not obey conventional spacetime limitations. Experiments have demonstrated entanglement with distances exceeding hundreds of kilometers, with no delay in information exchange. This instantaneous correlation raises profound questions. Is information traveling faster than light, or is there a deeper connection at play? One that transcends our classical understanding of space and time. Some physicists propose that entanglement could hint at the existence of a hidden layer of reality where time does not function in the conventional sense. If entanglement allows for faster-than-light connections, could it enable information transfer across time as well? This idea has led to speculation that entangled particles might be used as a form of quantum communication, capable of transmitting information not only across space but also through time itself. One of the most discussed proposals involves quantum teleportation. Quantum teleportation does not involve the physical transfer of matter, but rather the instantaneous transfer of information from one particle to another. This process has been experimentally verified, showing that quantum states can be transmitted without direct contact. If this principle could be extended to temporal transmission, it might offer a mechanism for sending information into the past or future. However, there is a major obstacle. Entanglement alone does not allow for the controlled transfer of usable information. When one particle is measured, its state becomes definite, but this does not inherently send a message that can be decoded without additional classical communication. Despite this limitation, some researchers suggest that further advancements in quantum mechanics may reveal new ways to exploit entanglement for practical time-related applications. One approach involves using entanglement to stabilize wormholes. Some theoretical models suggest that entangled particles could be linked through a non-traversable wormhole, effectively creating a shortcut through spacetime. If such a connection could be manipulated, it might be possible to establish a form of time travel using entanglement as a bridge. This idea, known as the ER equals EPR conjecture, proposes that entangled particles and wormholes are fundamentally connected, offering a potential quantum foundation for time manipulation. Another area of exploration is the relationship between entanglement and quantum time crystals. Time crystals are a recently discovered phase of matter that exhibit periodic motion without energy loss, seemingly defying traditional thermodynamic principles. Some researchers speculate that entangled time crystals could be used to encode information in a way that preserves past states indefinitely, potentially allowing for the retrieval of quantum information from different points in time. Could entanglement be harnessed to create a quantum system that operates beyond the constraints of linear time? Some physicists argue that if time is an emergent property rather than a fundamental one, then manipulating quantum states might provide a means of influencing time's progression. If quantum mechanics truly allows for non-local interactions, then time itself may be less rigid than previously assumed. The past, like the future, is indefinite and exists only as a spectrum of possibilities. These words from physicist Stephen Hawking capture the essence of the quantum world, where multiple timelines may coexist until an observation collapses them into a single reality. If time exists as a series of quantum probabilities rather than a fixed sequence of events, then entanglement might offer a means of accessing or altering those probabilities. Beyond theoretical physics, quantum entanglement is already being explored for practical applications in cryptography and computing. Quantum encryption relies on entangled particles to create unbreakable security codes, while quantum computers use entanglement to process information exponentially faster than classical computers. If these technologies continue to develop, they may eventually unlock new methods of interacting with time at the quantum level. Despite its potential, the study of entanglement and its connection to time travel remains in its infancy. Many of the ideas surrounding quantum time communication are highly speculative and require significant breakthroughs before they can be tested experimentally. However, the fact that entanglement already challenges our understanding of time and causality suggests that deeper insights may yet be uncovered. If entanglement does play a role in time travel, what would be the consequences? Would it allow for controlled, precise manipulation of events, or would it introduce unpredictable fluctuations in the fabric of reality? The implications stretch beyond physics, touching on philosophy, ethics, and even the nature of free will. Time travel, if feasible, would not simply be a scientific achievement. It would redefine our perception of existence itself. Could the laws of quantum mechanics provide a bridge between past, present, and future? If entanglement allows particles to share information instantaneously, then perhaps the boundary between time and space is not as rigid as it seems. The role of quantum entanglement in time travel remains one of the most profound and enigmatic questions in modern physics. Whether or not it ultimately leads to practical time manipulation, its existence alone forces us to rethink our understanding of the universe. Time, once thought to be an immutable force, may instead be a flexible construct shaped by the strange and unpredictable dance of quantum particles. The search for answers continues. As quantum mechanics advances, so too does our ability to probe the fundamental nature of time. If entanglement is a key to unlocking time's mysteries, then the future of physics may hold possibilities far beyond our current comprehension. Time travel. Fact or fiction? Time travel. A concept that has captivated the human imagination for centuries, inspiring countless theories, stories, and scientific inquiries. But is it merely a product of science fiction? Or does modern physics suggest that time travel might one day become a reality? While theoretical physics has proposed several mechanisms that could allow for movement through time, the question remains, is time travel truly possible, or are the obstacles simply insurmountable? To assess the feasibility of time travel, it is essential to examine the current state of research and experimentation. While no confirmed evidence of time travel exists, physics has provided some intriguing possibilities. General relativity, quantum mechanics, and advanced theories such as string theory all hint at ways in which the rigid flow of time might be altered. Yet each proposal is met with significant scientific and technological challenges. One of the most well-known time travel theories comes from general relativity, which suggests that under certain conditions, space-time can be warped in such a way that time loops or shortcuts, known as closed timelike curves, CTCs, can form. CTCs would, in theory, allow an object to return to its own past, creating the foundation for time travel. Theoretical physicist Kurt Gödel was one of the first to discover solutions in Einstein's equations that permitted such curves, suggesting that the rotation of a massive object could twist spacetime enough to create pathways through time. However, these solutions exist purely as mathematical possibilities. No natural structures in the universe have been observed that would create such effects, and the energy requirements to artificially generate a CTC are believed to be far beyond what is currently achievable. Additionally, the introduction of CTCs raises severe logical problems, such as the well-known grandfather paradox. What happens if someone travels back in time and alters the past in a way that prevents their own existence? Some physicists propose that nature may enforce a cosmic censorship principle that prevents such paradoxes from occurring. One such idea, known as the Novikov self-consistency principle, suggests that any action taken by a time traveler in the past would have already been incorporated into history in a way that prevents contradictions. In this view, time travel would be possible, but events would always unfold in a self-consistent manner, preventing any reality-breaking changes. But if time loops and CTCs remain speculative and potentially forbidden by unknown physical laws, could other forms of time travel exist? Some researchers have looked toward quantum mechanics for answers, particularly in the context of quantum superposition and the many worlds interpretation. Quantum superposition allows particles to exist in multiple states simultaneously until they are observed. Some theorists have speculated that if time were treated as a quantum variable, it might be possible to manipulate these superpositions to interact with different points in time. However, this remains entirely theoretical, with no experimental evidence to support the idea that time can behave in this way. The many worlds interpretation of quantum mechanics, on the other hand, suggests that every possible event creates a new branching timeline. If true, then altering the past might not change the present but would instead create an entirely new timeline, diverging from the original. If a method of traversing between these timelines could be developed, it might function as a form of time travel, though not in the traditional sense of revisiting one's own past. Even if theoretical physics allows for time travel under certain conditions, the technological barriers remain immense. One of the most fundamental challenges is the sheer amount of energy that would be required. Many proposed time travel methods, such as wormholes or Alcubierre warp drives, necessitate exotic matter or negative energy, substances that are currently beyond our ability to produce in significant quantities. Additionally, the stability of any time travel system presents a significant challenge. Even if a traversable wormhole or a functional time machine could be created, its sensitivity to external influences could render it unusable. Quantum fluctuations, gravitational disturbances, or even minor shifts in energy levels could collapse the structure, making sustained time travel nearly impossible. Beyond the technical limitations, there is the issue of information preservation. If time travel were possible, what would happen to causality? Would altering the past erase the present as we know it? Could information be sent back in time without disrupting the natural progression of events? These questions have no clear answers, and many physicists argue that the very nature of time might prohibit such interactions from occurring. Yet, despite these challenges, researchers continue to explore the limits of time and space. Theoretical physics thrives on pushing boundaries, and while time travel remains highly speculative, new discoveries in quantum mechanics, relativity, and high-energy physics could one day offer new insights. Some scientists even suggest that time travel experiments may already be occurring at the quantum level, where particles exhibit behavior that defies classical notions of time. One possibility being investigated is the use of quantum computers to simulate time travel scenarios. Some quantum experiments have suggested that quantum systems can retroactively influence their states based on future measurements, a phenomenon sometimes referred to as quantum retrocausality. While not equivalent to macroscopic time travel, these effects hint at the possibility that time is more flexible at the quantum level than previously believed. If time travel were ever to be realized, what would the consequences be? Would it revolutionize our understanding of history and the universe, or would it introduce risks that humanity is unprepared to handle? The potential implications stretch far beyond science, affecting philosophy, ethics, and even human civilization itself. Would access to the past allow for the correction of historical mistakes? Or would it open the door to dangerous alterations in the timeline? Would time travel be restricted to scientific use, or could it become a tool for political or personal gain? If time travel to the future became possible, what would this mean for our perception of progress, fate, and destiny? Despite the many unknowns, one thing is certain. The study of time remains one of the most fascinating and complex challenges in modern physics. Whether time travel ultimately proves possible or remains an unattainable dream, its exploration continues to push the boundaries of human knowledge. The search for answers is far from over. As scientific advancements continue, our understanding of time may evolve in ways that are currently unimaginable. Whether or not we will ever step into a time machine, the study of time travel forces us to confront the deepest questions about reality, existence, and the limits of human potential. For now, time travel remains a theoretical frontier, balanced between the realms of possibility and impossibility. But as history has shown, what once seemed impossible has often become reality through the relentless pursuit of knowledge. Perhaps one day, time itself will reveal its secrets, unlocking pathways to the past and future in ways we have yet to comprehend. Closing thoughts and potential implications. Time. A concept so deeply ingrained in human existence that it defines our perception of reality itself. From the ticking of a clock to the vast cosmic cycles that govern the universe, time is an ever-present force, seemingly immutable and irreversible. Yet, as we have explored throughout this discussion, modern physics suggests that time may not be as rigid as it appears. The theories of relativity, quantum mechanics, and speculative models of spacetime manipulation all hint at the possibility that time travel, though still a distant dream, may not be entirely beyond reach. But what would it mean for humanity if time travel became a reality? Would it be a scientific triumph that unlocks new dimensions of knowledge? Or would it introduce complications that could unravel the very fabric of our existence? The implications of time travel stretch far beyond theoretical physics, raising profound questions about causality, free will, ethics, and even the fundamental nature of the universe. To understand the full scope of these implications, we must first consider what time travel would mean for our perception of reality. If time is not an absolute, unidirectional flow but rather a malleable construct that can be traversed, then many of our assumptions about the universe must be reevaluated. The concept of cause and effect, which forms the basis of scientific reasoning, would need to be reconsidered. If actions taken in the future could influence the past, would our understanding of history remain valid? Or would it become an ever-changing sequence of events dictated by those with access to time travel technology? One of the most intriguing possibilities posed by time travel is the potential for communication across different points in time. If a means of sending messages into the past or future were discovered, it could revolutionize our ability to predict and prepare for events before they occur. Scientific breakthroughs, disaster prevention, and even advancements in medicine could be dramatically accelerated. But this also raises a troubling question. Would such a capability be used responsibly, or would it lead to unintended consequences? The concept of time loops further complicates this discussion. If time travel allows for interaction with the past, would it be possible to create an infinite cycle where knowledge or technology is passed back and forth without ever being truly discovered? The implications of such a loop challenge our understanding of progress and innovation. If an individual from the future provides blueprints for an advanced technology to someone in the past, who then develops that technology, where did the original idea come from? This paradox, known as the bootstrap paradox, suggests that time travel could create self-sustaining knowledge that has no clear point of origin. Beyond scientific and philosophical considerations, the ethical ramifications of time travel are immense. If individuals or organizations had the power to alter history, how could we ensure that this power was not abused? Would time travel become a tool for rewriting the past to serve political or personal interests? Would historical injustices be rectified, or would new forms of manipulation arise, leading to an even greater level of control over reality itself? Moreover, the potential existence of multiple timelines adds another layer of complexity. If time travel does not alter a single timeline but instead branches into parallel realities, would travelers merely be shifting between different versions of history? If so, would their actions have any real meaning, or would they be creating new, isolated worlds that exist independently of their original reality? These questions highlight the profound uncertainties surrounding time travel, making it clear that, even if it were possible, it would not be a straightforward scientific achievement. The ability to navigate time would require not only technological advancements but also a deep understanding of its consequences and ethical implications. Despite these challenges, the pursuit of time travel remains one of the most exciting frontiers in physics. Even if practical time travel proves impossible, the exploration of time's nature continues to push the boundaries of human knowledge. The study of wormholes, quantum entanglement, and temporal mechanics is already leading to advancements in fields such as quantum computing, cryptography, and high-energy physics. Stephen Hawking once remarked, "We are all time travelers moving at the speed of time into the future." While this statement reflects the natural progression of time as we currently understand it, it also hints at the possibility that the future of science may hold new ways of interacting with time itself. Perhaps the greatest lesson from the study of time travel is not that we may one day move backward and forward through history, but that our understanding of time is still incomplete. As research continues, new discoveries may reshape our perception of time, revealing aspects of reality that are currently beyond our comprehension. Whether or not time travel ever becomes a reality, the exploration of these concepts drives humanity closer to answering some of the most profound questions about existence. The mysteries of time are far from solved. The universe, vast and full of unknown possibilities, continues to challenge our understanding. As we look to the future, one thing is certain: the search for answers will never cease. Time travel, whether fact or fiction, remains a powerful symbol of human curiosity, a testament to our relentless pursuit of knowledge. Perhaps, one day, the secrets of time will be unlocked, and with them, new possibilities will emerge that reshape our understanding of the universe. Until then, the journey of discovery continues, guided by the fundamental question that has driven scientific exploration for centuries: what is the true nature of time?